In mathematics, a power of 2 means a number of the form 2n where n is an integer, that is the result of exponentiation with number 2 as the base and integer n as the exponent. In a context where only integers are considered, n is restricted to non-negative values, so we have 1, 2, and 2 multiplied by itself a certain number of times. Because 2 is the base of the binary numeral system, powers of 2 are common in computer science. Written in binary, a power of 2 always has the form 100 0 or 0.00 01, just like a power of 10 in the decimal system. Expressions and notations, verbal expressions, mathematical notations, and computer programming expressions using a power operator or function include 2 to the n, 2 to the power of n, 2 power n, power, 2, n, pow, 2, n, 2n, 1n, 2n, 2n, 2, 3, n, 2an. Computer science, 2 to the power of n, written as 2n, is the number of ways the bits in a binary word of length n can be arranged. As in unsigned integers, these ways represent numbers from 0 a 000 to 2n a 111 a 111, inclusively. Corresponding signed integer are positive, negative numbers, and 0. See signed number representations. Either way, 1 less than a power of 2 is often the upper bound of an integer in binary computers. As a consequence, numbers of this form show up frequently in computer software. As an example, a video game running on an 8-bit system might limit the score or the number of items the player can hold to 255 the result of using a byte, which is 8 bits long, to store the number, giving a maximum value of 28 to 1 equals 255. For example, in the original Legend of Zelda, the main character was limited to carrying 255 rupees at any given time, and the video game Pac-Man famously shuts down at level 255. Powers of 2 are often used to measure computer memory. A byte is now considered to be 8 bits. The prefix kilo, in conjunction with byte, may be, and has traditionally been, used to mean 1024. However, in general, the term kilo has been used in the International System of Units to mean 1000. Binary prefixes have been standardized, such as kibia, key, meaning 1024. Nearly all processor registers have sizes that are powers of 2, 32 or 64 being most common. Powers of 2 occur in a range of other places as well. For many disk drives, at least one of the sector size, number of sectors per track, and number of tracks per surface is a power of 2. The logical block size is almost always a power of 2. Numbers which are not powers of 2 occur in a number of situations such as video resolutions, but they are often the sum or product of only 2 or 3 powers of 2, or powers of 2 minus 1. For example, 640 equals 512 plus 128 equals 128 5, and 480 equals 32 15. Put another way, they have fairly regular bit patterns. Mersenne primes, a prime number that is 1 less than a power of 2 is called a Mersenne prime. For example, the prime number 31 is a Mersenne prime because it is 1 less than 32. Similarly, a prime number that is 1 more than a positive power of 2 is called a Fermat prime. The exponent will itself be a power of 2. A fraction that has a power of 2 as its denominator is called a dyadic rational. The numbers that can be represented as sums of consecutive positive integers are called polite numbers. They are exactly the numbers that are not powers of 2. Euclid's Elements, Book 9, The Geometric Progression 1, 2, 4, 8, 16, 32, is important in number theory. Book 9, Proposition 36 of Elements proves that if the sum of the first n terms of this progression is a prime number, then this sometimes the nth term is a perfect number. For example, the sum of the first 5 terms of the series 1 plus 2 plus 4 plus 8 plus 16 equals 31, which is a prime number. The sum 31 multiplied by 16 equals 496, which is a perfect number. Book 9, Proposition 35, proves that in a geometric series if the first term is subtracted from the second and last term in the sequence, then as the excess of the second is to the first, so will the excess of the last be to all of those before it. Applying this to the geometric progression 31, 62, 124, 248, 496, we see that 62 minus 31 is to 31 is 496 minus 31 is to the sum of 31, 62, 124, 248. Therefore the numbers 1, 2, 4, 8, 16, 31, 62, 124 and 248 add up to 496, and further these are all the numbers which divide 496. For suppose that p divides 496 and it is not amongst these numbers. Assume par euro q is equal to 16 a euro a euro 31, or 31 is to q as p is to 16. Now p cannot divide 16, or it would be amongst the numbers 1, 2, 4, 8 or 16. Therefore 31 cannot divide q. And since 31 does not divide q and q measures 496, the fundamental theorem of arithmetic implies that q must divide 16 and be amongst the numbers 1, 2, 4, 8 or 16. Let q be 4, then p must be 124, which is impossible since by hypothesis p is not amongst the numbers 1, 2, 4, 8, 16, 31, 62, 124 or 248. The first 96 powers of 2, sequence A000079 in OEIS, one can see that starting with the 2 the last digit is periodic with perioda 4, with the cycle 2 a euro 4 a euro 8 a euro 6 a euro, and starting with the 4 the last 2 digits are periodic with perioda 20. These patterns are generally true of any power, with respect to any base. The pattern continues, of course, where each pattern has starting point 2k, and the period is the multiplicative order of 2 a modulo of 5k, which is I, 5k, a equals a4aa, a5 car1. Powers of 1024, sequence A140300 in OEIS, the first few powers of 210 are a little more than those of 1000, see also IEE 1541 to 2002. Powers of 2 whose exponents are powers of 2, because data and the addresses of data are stored using the same hardware, and the data is stored in one or more octets, double exponentials of 2 are common. For example, sequence A00146 in OEIS, 21 equals 2, 22 equals 4, 24 equals 16, 28 equals 256, 216 equals 65,536, 232 equals 4,294,967,296, 264 equals 184467440737095511616, 2128 equals 3402823669209384634633, 374607431768211456, 2256 equals 11579208923731619543, 5709850086879078532669. 984665640564039457584007, 913129, 639936, 2512 equals 13407807929942597099, 5740249982058461274779. 36582059233777235614437231, 443721764, 030, 073, 54697680187429816690 4276900318581864864050. 8537538828119465699946, 433, 649,006,084,096, 21,024 equals 179769313486231590772, 931. 304835356329624224137, 216, 22,048 equals 323170060713110073007, 148. 19355583611059596230, 656, 24,096 equals 104438888141315250669, 175. 2430470834040315419, 336, 28,192 equals 109074813561941592946, 298. 997186505665475715792, 896, 216,384 equals 118973149535723176508, 576. 46044702729066996406, 816, 232,768 equals 141546103104495478900, 155. 5411226681046337123777, 856, 265,536 equals 200352993040684646497, 907. 339445878895905719156, 736. Several of these numbers represent the number of values representable using common computer data types. For example, a 32-bit word consisting of 4 bytes can represent 232 distinct values, which can either be regarded as mere bit patterns, or are more commonly interpreted as the unsigned numbers from 0 to 232 or 1, or as the range of signed numbers between a 231 and 231 or 1. Also see titration and lower hyperoperations. For more about representing signed numbers, see 2's complement. In a connection with numbers, these numbers are often called format 2 powers. The numbers form an irrationality sequence. For every sequence of positive integers, the series converges to an irrational number. Despite the rapid growth of this sequence, it is the slowest growing irrationality sequence known. Some selected powers of 2, 28 equals 256, the number of values represented by the 8 bits in a byte, more specifically termed as an octet. 210 equals 1024, the binary approximation of the kilo, or 1000 multiplier, which causes a change of prefix. For example, 1024 bytes equals 1 kilobyte. This number has no special significance to computers, but is important to humans because we make use of powers of 10. 212 equals 4096, the hardware page size of Intel x86 processor. 216 equals 65,536, the number of distinct values representable in a single word on a 16-bit processor, such as the original x86 processors. The maximum range of a short integer variable in the C and Java programming languages. The maximum range of a word or small int variable in the Pascal programming language. 220 equals 1,048,576, the binary approximation of the mega, or 1 million multiplier, which causes a change of prefix. For example, 1,048,576 bytes equals 1 megabyte. This number has no special significance to computers, but is important to humans because we make use of powers of 10. 224 equals 16,777,216, the number of unique colors that can be displayed in true color, which is used by common computer monitors. This number is the result of using the 3-channel RGB system, with 8 bits for each channel, or 24 bits in total. 230 equals 1,073,741,824, the binary approximation of the giga, or 1 billion multiplier, which causes a change of prefix. For example, 1,073,741,824 bytes equals 1 gigabyte. This number has no special significance to computers, but is important to humans because we make use of powers of 10. 231 equals 2,147,483,648, the number of non-negative values for a signed 32-bit integer. Since Unix time is measured in seconds since January 1, 1970, it will run out at 2,147,483,647 seconds or 3:14 and 7 seconds UTC on Tuesday 19 January 2038 on 32-bit computers running Unix, a problem known as the year 2038 problem. 232 equals 4,294,967,296, the number of distinct values representable in a single word on a 32-bit processor. Or, the number of values representable in a double word on a 16-bit processor, such as the original x86 processors. The range of an int variable in the Java and C programming languages. The range of a cardinal or integer variable in the Pascal programming language. The minimum range of a long integer variable in the C and C++ programming languages. The total number of IP addresses under IPv4. Although this is a seemingly large number, IPv4 address exhaustion is imminent. 240 equals 1,999,627,776, the binary approximation of the Theorem, or 1 trillion multiplier, which causes a change of prefix. For example, 1,999,511,627,776 bytes equals 1 terabyte. This number has no special significance to computers, but is important to humans because we make use of powers of 10. 250 equals 11258999068426224, the binary approximation of the peta, or 1000000000000 multiplier. 11258999068426224 bytes equals 1 petabyte. 260 equals 11529215046068469776, the binary approximation of the exa, or 1000000000000 multiplier. 11529215046068469776 bytes equals 1 exabyte. 264 equals 184467440737095511616, the number of distinct values representable in a single word on a 64-bit processor. Or, the number of values representable in a double word on a 32-bit processor. Or, the number of values representable in a quad word on a 16-bit processor, such as the original x86 processors. The range of a long variable in the Java and C programming languages. The range of a int64 or quad variable in the Pascal programming language. The total number of IPv6 addresses generally given to a single LAN or subnet. One more than the number of grains of rice on a chessboard, according to the old story, where the first square contains 1 grain of rice and each succeeding square twice as many as the previous square. For this reason the number 264 is known as the chess number. 270 equals 1180591620717411303424, the binary approximation of iota, or 1000000000000 multiplier, which causes a change of prefix. For example, 1180591620717411303424 bytes equals 1 yottabyte. 286 equals 77371252455336267181, 195,264. 286 is conjectured to be the largest power of 2 not containing a zero. 296 equals 79228162514264337593. 543,950,336, the total number of IPv6 addresses generally given to a local Internet registry. In CIDR notation, ISPs are given a /32, which means that 128 minus 32 equals 96 bits are available for addresses. Thus, 296 addresses. 2128 equals 3402836669209384634663, 374607431768211456, the total number of IP addresses available under IPv6. Also the number of distinct universally unique identifiers. 2333 equals 174980057982640953949. 9800178169409709222825, 35544714569941406164, 851,279,623. 993595007385788105416, 184,430,592. The smallest power of 2 which is greater than a Google. 257,885,161 equals 58188266232246442175, 100. 725746141988071724285, 952, one more than the largest known prime number as of 2013. It has more than 17 million digits. Fast algorithm to check if a positive number is a power of 2, the binary representation of integers makes it possible to apply a very fast test to determine whether a given positive integer x is a power of 2, positive x is a power of 2a is equal to 0. Where and is a bitewise logical AND operator. Note that if x is 0, this incorrectly indicates that 0 is a power of 2, so this check only works if x greater than 0. Examples: proof of concept. Proof uses the technique of contrapositive statement, S, if x and x1 equals 0 and x is an integer greater than 0 then x equals 2k. Concept of contrapositive, S1, PQ is same as S2, QP, in above statement S1 and S2 both are contrapositive of each other. So statement S can be restated as below, S if x is a positive integer and x a permel 2k x and x1, a permel O proof, if x a permel 2k then at least 2 bits of x are set. Let's assume m bits are set. Now, bit pattern of x, 1 can be obtained by inverting all the bits of x up to first set bit of x. Now, we observe that expression x and has all the bits 0 up to the first set bit of x, and since x and has remaining bits same as x and x has at least 2 set bits, hence predicate x and a permel 0 is true. Fast algorithm to find a number modulo a power of 2, as a generalization of the above, the binary representation of integers makes it possible to calculate the modulos of a non-negative integer with a power of 2 very quickly, x mod y equals. Where and is a bitewise logical AND operator. This bypasses the need to perform an expensive division. This is useful if the modulo operation is a significant part of the performance-critical path, as this can be much faster than the regular modulo operator. Algorithm to convert any number into nearest power of 2 number. The following formula finds the nearest power of 2, on a logarithmic scale, of a given value x greater than 0. This should be distinguished from the nearest power of 2 on a linear scale. For example, 23 is nearer to 16 than it is to 32, but the previous formula rounds it to 32, corresponding to the fact that 23/16 equals a 1.4375, larger than 32/23 equals a 1.3913. If x is an integer value, following steps can be taken to find the nearest value in a computer program. Find the most significant bit position k, that is set from the binary representation of a x, when 1 means the least significant bit, then, if bit ka1 is 0, the result is 2k. otherwise the result is 2 car euro plus a euro 1. Algorithm to round up to power of 2, sometimes it is desired to find the least power of 2 that is not less than a particular integer, n. The pseudocode for an algorithm to compute the next higher power of 2 is as follows. If the inputs is a power of 2, it is returned unchanged. Whereas a binary OR operator is the binary right-shift operator, and bit space is the size of the integer space represented by n. For most computer architectures, this value is either 8, 16, 32, or 64. This operator works by setting all bits on the right-hand side of the most significant flagged bit to 1, and then incrementing the entire value at the end so it rolls over to the nearest power of 2. An example of each step of this algorithm for the number 2689 is as follows. As demonstrated above, the algorithm yields the correct value of 4096. The nearest power to 2689 happens to be 2048. However, this algorithm is designed only to give the next highest power of 2 to a given number, not the nearest. Another way of obtaining the next highest power of 2 to a given number independent of the length of the bit space is as follows. Other properties, the sum of all n choose binomial coefficients is equal to 2n. Consider the set of all n-digit binary integers. Its cardinality will be 2n. It will also be the sums of the cardinalities of certain subsets, the subset of integers with no ones, the subset with a single one, the subset with 2 ones, and so on up to the subset with n ones. Each of these is in turn equal to the binomial coefficient indexed by n and the number of ones being considered. The number of vertices of an n-dimensional hypercube is 2n. Similarly, the number of faces of an n-dimensional cross-polytope is also 2n, and the formula for the number of x faces an n-dimensional cross-polytope has is: the sum of the reciprocals of the powers of 2 is 2. The sum of the reciprocals of the squared powers of 2 is 1a. See also, binary number, geometric progression, integer binary logarithm, inchworm song, octave, sum free sequence, references. External links: Sloan's A000792N, the online encyclopedia of integer sequences. OEIS Foundation. Sloan's A00114622, 2N, the online encyclopedia of integer sequences. OEIS Foundation.